how do I usually study something new like this? The first thing I will ask myself is, can I explain, if I'm learning this for the first time, I'll ask, what is it? And basically, I want to ask myself, can I explain this to a layman or who has never done physics before? Or can I explain this to an 8-year-old, sort of the 8-year-old test? Einstein used to famously say this, right? So if you cannot explain a concept in simple words to an 8-year-old, you don't understand it enough yourself. So it's always a good test to try to do this. So what is a capacitor to an 8-year-old? I think it's very simple. All you have to say is, it's basically the world's simplest power bank, basically. It's a good thing nowadays 8-year-old would probably know what a power bank is. It's a rechargeable battery. So that's it, right? The second thing you might want is to know the technical side of things, okay? So that's the first thing you want to get a good understanding, but so that's just a device. It's a device which is a rechargeable battery, but the real concept is capacitance, right? The physics concept is capacitance. So the first thing, what is it? What is capacitance? Well, capacitance, I'm not going to write it, maybe I will, is how powerful your device is, right? So it's how powerful, how much charge it can hold your devices, all right? So go into the technical side, ask yourself, what's the word definition and what's the equation definition? This is how I would study, right? So each time you encounter a new concept like this, the word definition or the equation definition is, it's the amount of charge you hold per potential difference, right? Each volt, how much charge you can hold. So also you will need to know the symbol and the SI base unit, which will help you to solve problems. So this is farads, okay? So the symbol is C. So remember, definitions mean defining new concepts in terms of old concepts. So we're defining, by now you know what a potential difference is and you know what charge is. And so the word definition is just the amount of charge stored per potential difference. I'm not going to write that in full. And before you study physics, you look at a power bank, you might think that, oh, I need to know a lot of advanced chemistry or a lot of maybe engineering, electronics to know how a power bank works. Turns out, no, you already know with what you've learned so far. All you need is 2 parallel plates. This is the simplest way to construct a power bank. Nowadays, people do is take these 2 plates, or let me go through the basics first. You connect it to some power source to charge it up like a battery. The symbol for a capacitor is 2 parallel plates. For the battery is 1 longer leg and a shorter leg. The shorter leg looks like a minus sign, so that's how I remember one side is positive, one side is negative. That's the positive terminal and negative terminal, like that. So what it does is, if I have a positive charge over here, also if you ask yourself what's a battery, if you study chemistry, it will be a very complicated answer involving ions and molecules and chemical reactions and stuff like that. You ask an electronic engineer, they'll give you another complicated answer. But for physics, we keep things very simple. A battery is basically a device that sets up a battery is a device that sets up a potential difference. That's it. It creates a potential difference between its 2 terminals. So what that means is, let's say you connect a 9-volt battery. If you have a 9-volt battery, it means that one side is 0 volts and the other side is 9 volts. The absolute potential on one side is 0. The absolute potential on one side is 9. So the potential difference is 9 minus 0 equals 9, right? So what is the use for that is, if I have one side is 0 volt, one side is 9 volts, then positive charges would always go from which way to which way? They'll go from high potential to low potential. So all the positive charges would start flowing from high potential to low potential this way. However, there is a gap between here, so it will get stuck over here. So all the positive charges would get accumulated over here, and you can either think of all the positive charges get sucked over here, leaving with negative charge, or the positive charges that build up, let's say a total of Q that's built up over here, will suck all the negative charge, assuming the wire is an ideal wire, like an ideal conductor, which means conductor means charges are free to move. So if you have positive charges here, it will suck all the negative charges here and repel all the positive charges this way, right? So you will build up an amount of negative charge. How much negative charge? Precisely minus Q. You won't build up anything more than minus Q because you only have positive Q here. If you attract less than minus Q, it will keep attracting until it's saturated like this, right? So what Q do you plug in here? Do you plug in the positive side or the negative side, or do you plug in the total? Some people might think you plug in the total charge, but that's wrong, right? You can't plug in a total because if you plug in a total, it will be 0. If you add positive Q plus minus Q or 2Q, right? That's not the right one. You plug in only the positive, either the positive side, or you plug in the magnitude of either side. You put an absolute value, and then you plug in one side of the charge. It's asking how much charge builds up on one side. It's the absolute value of charges build up on one particular side. Okay? So nowadays, capacitors are not made of two parallel plates like this. What they might do is take one plate and curl it up like this, and take a second plate like this and curl it up so that they're just not touching. So now you have a little cylindrical device like this that you can two plates are curled like this, and then you can have lots of these mini capacitors and put it in one rectangular device, and then you can sell it on Amazon. And that's how you have power banks like this. But it's basic. The basics is just two parallel plates. So how do you analyze this? Now let me draw a capacitor. This is how I will solve all the problems with capacitors. Let's say I have what I do is I always label the Q and minus Q, right? One side is plus Q, one is minus Q. And I also write down what is the potential difference across the two sides. You see potential difference is always across two sides. So I like the word delta because that tells me the difference. Now, imagine instead of the two wires like this, I'm going to split my wire up. Nothing's going to change, right? Nothing fundamentally is going to change. The difference is still delta V, right? There's still positive Q and negative Q here. But now I'm going to take a scissors and cut it straight through like this. And now I have basically built up a parallel situation over here. And you've seen a lot of, so how do we analyze this? So now I have one capacitor on top and a second capacitor on the bottom. So I'm going to label Q2 minus Q2, Q1 minus Q1. And I'm also going to label the potential difference across these guys. Immediately, you can tell, let me bring the two plates a little bit closer. Maybe a little bit more closer. Just for aesthetics. You can tell that V1 has to equals to V2 because your V1 is the difference between these 2 points. But these 2 points are exactly the same as these 2 points, right? I should say this point is the same as this point, right? If you have an ideal wire, there should be no potential difference between here. You've learned in the next chapter, any potential difference or anything that has resistance is given by this. So if the resistance of the wire is 0, there is no potential difference between these two orange points. And between these two orange crosses, again, if there's no resistance between them, the potential difference between here is 0. So the absolute potential between these two are the same. The absolute potential is here is the same. So immediately you will deduce that if you have parallel configurations, you will have this situation going on. Also, notice that this point is the same as this point, and this cross is the same as this cross. So if this difference is V1, then this difference is also V1. So they're all the same, right? So whenever you have a parallel configuration, this is what you can deduce. Should you memorize this? No. Learn how to draw the diagram over here. If you can draw this diagram, I hope from what I have discussed, you see how easy it is to look at the difference between here. How about the charge? Can I relate the charge? Yeah, because remember the whole side was actually Q, right? So Q1 and Q2 was actually this. I just cut this in half, right? So nothing was fundamentally changed. I just split the two wires like this, and then I just cut it in half. So this plus this has to equals to this. So we have a relationship, Q1 plus Q2 is Q. Should you memorize this for parallel configuration? Again, no, it should be obvious from here. Now, you also remember the definition of any capacitor is how much charge it holds. So let's apply the definition in here and see what we find. For example, on this side, I find Q1, C1, Q2, C2 equals Q over C. On this side, if I plug it in, I find C1 delta V1 plus C2 delta V2 equals C delta V. But since all the delta V are the same, then this cancels out, which gives me C1 plus C2 equals C. So if I combine 1 and 2, you have this famous formula like this, and you've seen many times in your homework that for parallel cases, right? So this is a quick reminder. Should you memorize this blue one? Yes, I think so. When I study a topic, after I ask myself, can I explain it to a layman and what is the definitions? There's only 2 types of equations or formulas I will memorize for myself. One is definitions. You cannot, I know it's in the formula sheet, but you have to memorize it. Otherwise, it's like reading a novel. If you don't know the definition of words, it's like looking up the dictionary every word. You can't read a novel that way. You can't read a book that way. Right? You need to know definitions by heart. Otherwise, you'll struggle a lot. If you find yourself struggling in physics, that might be one reason. You don't know the definitions of words. So make sure every time electric field, electric potential, potential difference, potential energy, capacitance, voltage, everything. Voltage is just potential difference. That's why I like to call potential difference. It's more obvious what it means. Yeah, learn the definitions. The second type of equations that I will commit to memory is ones that are very useful, all right? And it's not easily deducible from a diagram. So you see that these two should be deducible from a diagram. Otherwise, in the capacitance chapter, you will have 6 equations you will have to remember. But now you should only have 3 equations you need to remember. You can't remember too many equations. I always try to keep the number of equations I memorize per chapter of the order around like 2 or 3 equations that I actually memorize. The others I learn to draw a diagram so that they'll deduce the relation. So you really understand what's going on. Okay. Now let me redraw this. This time, right? This time I'm going to I'm going to insert another piece of 2 metals connected by a wire. So everything in bold, in black in the middle, is just a neutral piece of metal, right? It might be copper wire and iron plates, but it's just metal. So if I have Q and minus Q here, suddenly I have made myself 2 capacitors in series. So how do I draw this? So I'll do the same thing like this. Do the same labeling. So for everything, label plus and minus Qi. For each capacitor, label its capacitance plus and minus Qi and its potential difference like this. I'll do the potential difference last. I'll do this first. So what can we say about the charges? For 1, I immediately know that Q is equals to Q1, right? It's just, this side is literally this side. I've just inserted a metal here. It's not going to change anything. This is the overall potential difference, right? So immediately on the left, I see that Q is equals to Q1. How about on the right? I see that minus Q2 is equals to minus Q, which just means Q is equals to Q2, right? But that means that Q1 is also equals to Q2. They're all equal, so I can simplify my relationship. It's actually also very obvious from here. If one side has negative Q1, the other side must be positive Q1. Right? So Q2 has to equal to positive Q1 because this whole thing was neutral. Okay. So if it is neutral, so if one side is minus Q1, the other side has to be minus Q1. So you see that the absolute value of Q1 and Q2 has to be the same, right? So this thing has to add up to 0. So that's the relationship for series. Contrast that with for parallel, right? So you see, for each case, I can come up with 3 equations. I can relate all the Q's and all the V's and all the C's. But I don't memorize these 2. I'll memorize the C. So I won't memorize this one. How about the delta V? Well, this is the difference, right, between V1, and this is the potential difference between the second capacitor. Just by staring at this, can you tell me a formula that relates all the V's, all the potential difference? Should be obvious, right? Let's say this is 3 volts. Let's say this is 5 volts. What is this? The difference must be 8 volts, right? So it is a very simple relationship like this. And finally, to link it up with find the relationship between the capacitors, I can plug that in. And what do I get here? I get C delta V equals C1 delta V1, right? So if you know how to write these out, you will be able to solve all the problems. Now I saw that all the Q's are the same, so these actually cancel out. And this is the famous formula you've seen many times in the books. When you have a series situation, the equivalence of 1 and 2 is basically given by this reciprocal summation, right? So the 2 in the box I will remember, plus the third one, the definition of what capacitance is, I'll definitely remember, right? So these are the 3 things I remember. These are useful. Even this one I wrote out is useful, for example, because if you know this and this and this, can you find delta V2? Can you find the potential difference here? Yes, right? If you know this and this, you can, yeah. So same thing. And then if you know this, you also be able. So all of these are useful, but I won't commit these to memory. I'll learn how to draw the diagram. So hopefully you've seen this is helpful. And finally, just to give you 2 more equations that is useful in the chapter. One is the energy that is stored inside a capacitor. The energy stored inside a capacitor is given by this, right? So I don't have time to explain where this comes from. I would love to, so you don't have to memorize this and you know where it comes from. But for now, I don't have time. So maybe this easy way is just to memorize the energy, electric potential energy that is stored inside a capacitor is given by this. You can use the definition and write out several different formats of this, right? But you can pick one of these to remember, and you can deduce the other two. Usually, technically, this is more fundamental, so I start with that, but it's up to you which one to memorize. One more thing is know that power. It's actually in the next chapter, but the definition is how much energy per unit time you have consumed. So this can be consuming electric potential energy or some work done or some amount of heat you add to a heat engine. That's how much energy per time. That's power. That's a definition of power. All right.